So we have a dam that's 100 feet high and 1,200 feet wide, filled to capacity with fresh water. Find the hydrostatic force on the dam, the pressures at the top and the bottom of the dam, and the location of the center of pressure relative to the water surface. So before I get right into this, I just want to say I've just had a ton of caffeine and I have not slept much. So we'll see how this goes, but everything should be correct if this is posted. So let's just get started. For part A, we want to find the hydrostatic force, which is Fr is equal to Pc times A. And if we look at Pc real quick, this is the pressure at the centroid. So Pc would be somewhere right about here, just right in the center of our dam. And I'm assuming our dam is just a rectangle, just completely flat and vertical. So for it being in the center, let me turn down my music a little bit. For it being in the center, we'll need to have this be this height over 2. So this distance will be 50 feet. And for this horizontal distance, it doesn't really matter because pressure is calculated by your difference in height. If this dam was angled a bit more, or I shouldn't say a bit more, if it was angled at all, then yeah, you would have to take that into account, in which case it would be 1,200 over 2, which is 600 feet. So how do we find the pressure at the centroid? So we're going to use one of the main equations, I think blue is good for this, is the hydrostatic equation, which is delta P is equal to rho GH. This is an equation you should get very, very familiar with if you're not already. What we can also write this as is gamma H. Gamma is the specific weight, and that is really helpful in the English system, which is what we are in right now. So before I calculate Pc, I just want to explain what gamma is and when you should use it. And gamma, you should really use it whenever you are in the English system, because if we have rho times g, so density, which is pound mass per cubic foot, times gravity, which is in feet per second squared, then this does not come out to be anything nice. What we can do, though, is we can use specific weight, because specific weight will be in pound force per cubic foot. But why would we even want that? Well, we're trying to get pressure, right? And pressure is just kind of defined generally. So pressure is defined as our force over our area. So over here with our rho g, let me write that again, rho g, you would have something that starts with pound mass. Pound mass is mass, that's not a force. So if we use gamma, then we'll get a force. So in the metric system, if you have, let's just say, a 100-meter high dam and a 1,200-meter wide dam, or 100-meter high, 1,200-meter wide dam, you could use gamma, but it doesn't have the same advantage, I guess, as it is in the English or imperial system. So the best way to kind of show that is just to calculate it. Because if we say that Pc, this is all coming from the hydrostatic equation right here, Pc is equal to the density of water, which is 62.4, so I'm using this part of the equation right now, pound mass per cubic foot. We multiply that by gravity, which you have to remember is 32.2 feet per second squared in the English system. Before I move on to our height, which we already know is 50, we've already covered that right on over here. We want to convert this into some sort of force. And remember, right here, this is our density. This is our density of the fluid. So how we convert rho g into gamma in the English system is we simply say that there's 1 pound force for every 32.2 pound mass times feet per second squared. It's just that easy. So we can go over here, we can actually cancel out our 32.2, and what we'll end up with is something on the lines of pound force per cubic foot. So if we just add on this 50 at the end, this would be 50 feet. So just condensing all of this down now, PC is equal to 62.4. Remember, because our gravity canceled out with our conversion rate right here. Again, this would not happen in the metric system. This is only happening in the English system. So that's why I'm allowed to do this. If I were to do this in the metric system, I would probably just stay with the rho GH, because gamma is just like, it's fine, it works, but it's not like groundbreaking as it is in the English system. So if I move this up a little bit, now we have 62.4 pound force per cubic foot multiplied by 50 feet. And now our feet cancel, leaving us with our answer in pound force per square foot, or this is also called PSF. So let me do that calculation real quick. So it's 62.4. 62.4 times 50. This would be around 3120 PSF. So that is our pressure at the centroid. And just a little bit more on pressure while we're at it. If this is a cross section of the dam, this right here is 100 feet high. How the pressure will be distributed as it goes down is kind of like this triangle, where you have a lot more pressure at the bottom of the dam, and it gets slowly, lesser and lesser as we go up. Why we're allowed to use this PC right here is because if we take the average pressure, then we have to take the average of where it's acting, and this right here is our PC. This is where it's acting on our dam itself. And if we were to take this whole blue area down here in this picture, this whole little blue triangle, and we were to kind of mirror it over here, it would fill up our average. So that's why we're allowed to do all of this. So all this is just a really, really good average. So we're in pounds, pound force per square foot. And let's keep it like that because our area is going to come out in square feet. So going back, FR is equal to 3120 pound force per square foot multiplied by our cross-sectional area of the dam, so 100 feet times 1,200 feet. 1,200 feet. And we have 2 feet being multiplied together, that's feet squared, which will cancel out with our denominator, leaving us with an answer in pound force. This is 100 times 1,200 times our pressure at the center, but not our center of pressure, just a pressure at the center. That is a very large number. I'm getting 3744. Is that like 10 divided by, let's see, 10 to the, oh, that actually was 10 to the 8th. Okay. So we're getting around 3.744 times 10 to the 8th pound force. So this is how much hydrostatic force is being acted on the dam just from the water being there on one side and the air being there on the other side. So this is part A. For part B, pressures at the top and the bottom of the dam. So let's tackle the top first. And actually, I'm going to draw that picture again. That picture will help us out a lot right here. So we have our we have our side view of the dam, and we have our pressure lines going all the way down. And our pressures decrease as we go up. So what we need to do is we need to find the pressure at the top. We need to find the pressure at the bottom. There's two ways you can get the pressure at the top, but there's really only one true way you can get the pressure at the bottom. The pressure at the top, it's actually just going to be 0 because, I mean, if you look at this picture, we're getting 0 gauge pressure. Like we are still in the atmosphere. We're at the very top of the dam. Nothing's really happening up there. So we can just have it at 0. If you want that in a mathematical way, if we do P top, and again, we're going to be using this hydrostatic equation right here, but this time I'm just going to skip everything and go straight to gamma. This would be gamma times our height. But our height at the top is actually 0. So this would be gamma times 0, which is 0. So this is our answer, and I'll put this in, let's put this in PSI because, I don't know, just kind of feel like it. I guess that's what caffeine does to you on a Friday afternoon. So we have 0 PSI. For the bottom, we're going to be using that same gamma, which, remember, gamma is a specific weight, and gamma is still going to be 62.4 pound force per cubic foot. So gamma times our height at the bottom. Our height at the bottom of the dam, remember, we are dealing with a 100-foot tall dam. So up here, this is at 0 feet. That's why we're able to plug in this 0. At the bottom of the dam, that means that we have a distance of 100 feet. So we can plug in 62.4 pound force per cubic foot for our gamma. You multiply that by 100 feet. We can cancel our units. We'll get 62.4 times 100. And yes, I am using calculator for that because I'm very tired. So we have 6240 pound force per feet squared, or PSF. Now, if I want to get this into PSI to match our top pressure, we could do 6240. So just rewriting pound force per foot squared. And now we can do, in 1 foot squared, we have 144 inches squared. Again, canceling units. So now we divide by 144. So this would give around 43.33 repeating. So 43.3 PSI. So that is part B complete. Now what do we need to find for part C? It is the location of the center of pressure relative to the water surface. So the center of pressure is described by this equation. That's not a gamma, this is a y. Y sub p is what we're looking for, is equal to y sub c plus I sub xx comma c, which I believe is our moment of inertia across the centroid, or something very similar to that moment of inertia about the centroid. I believe that's actually what it is. We have all that divided by y sub c times our area. Now, for our y sub c, just both of these terms right here, our y sub c is our exact same one that we used earlier as our h sub c. So I'm just going to rewrite this as h sub c, which we already know is 50 feet, plus 50 feet right over here, multiplied by our area, and I'm just going to fill that in because just standard cross-sectional area is all of this. So that's just our 100 times our 1200. So 100 feet times 1200 feet. All that over I x x comma c. So what is ix, or I sub xx comma c? How do we find that, I guess, is the best question. And that's something I messed up a lot on before, but I finally have gotten it down. It varies per shape. So hopefully on an exam you will not have to derive this. On my exams, I was given a few different ones. We were given some for triangles, some for circles or rectangles. In this case, we're just going to be using rectangles, which I do have with me. But the equation for the moment of inertia about the centroid is your length times your height cubed over 12. So in this case, let me actually just move this down a little bit. We have our length, which is 1200 feet. And then we multiply that by our height, which is 100 feet. And this is cubed. And we divide all of this by 12. So let's see what this will come out to. 1200 times 100 cubed divided by 12, and that is what times trying to figure out exactly how much. Oh, that's actually perfect. This is 1 times 10 to the 8th feet to the 4th. So we can go back to that main equation that we've been looking at right up here, and now we can plug in this number for I sub xx comma c. So this is 50 feet plus, actually I'm just going to copy all of this over. All of that, and we just replace the very top part with 1 times 10 to the 8th feet to the 4th power. Looking at the units at the bottom, we have feet times feet times feet, which is in cubic feet, and we have feet to the 4th on the top. So we can actually cancel out all of these, and we'll just be left with feet, Then we'll have feet on this side, and our final answer should be in feet, and this would be feet below the surface of the water. So plugging this in is 50 plus 1 times 10 to the 8th over 50 times 100 times 1200. And that gives 200 over 3, but I'm just going to plug 200 over 3 back in, and we should get 66.67 feet below the surface. So this is where the actual center of pressure is on the dam relative to the surface. So our center of pressure, if this is 50 feet, then it's a little bit more. So this is where a y sub p is relative to the surface, which is up here. I cannot believe I made it through that whole problem on strictly caffeine, but I believe that is problem complete.